Yeah, I'm going to be talking about accurate 3D mapping. I'm from a company, Fugo Roams, who our office is in Brisbane, Australia. And so Fugo is the holding company. They own they're multinational, owning a whole bunch of different companies, and Roams is the sort of startup that I'm involved in, among various other people. There's 2 other people here. Okay, so what we do is we capture large amounts of the Earth. We scan large amounts of the Earth with remote sensing technology and make a high-level view of, or a high-level representation of that scanned data available to infrastructure owners. So our main client at the moment is a large power line company, power line owner, and so we basically tell them about their assets, where they're too close to trees, and the trees keep growing every year, so we have to scan it every year. So the bits these are kind of the rough parts which are the rough set of things which we do. So we are involved in the data capture. We have sensor kits. We put them under a Cessna and fly them around with LiDAR and cameras on them. So for anyone who doesn't know, LiDAR is a laser ranging instrument, so it sends out laser pulses and using the time of flight it can tell the depth. So we process the raw data off those instruments, and that involves, well, I'll go into the details of some of these things in a minute. But this is just raw data to start with. It's pixels and point clouds. So there's not much you can do with that directly. Other than look at it, and if you have 150,000 kilometers worth of power lines, some sort of millions of poles and millions of lines, then just looking at the data by eye is not going to do much good for you. So we process the raw data and produce point clouds and imagery. Then we go and detect features on top of that. So these are things like power lines and poles, as I was saying. This is a point cloud. You can see there's lots of other things in there. Using the high-level features that we get, we can do physical modeling and risk analysis and stuff. Okay, so to give you a better idea of what's here, this is what I forgot to do before. Okay, so this is the point cloud. We've overlaid the color from the camera on top of it. So you can see that there's some of these things. Well, the color doesn't look very good on the power lines. There's some interesting features which are quite visible. So that's what that looks like. That's the point cloud data. It's just a bunch of points in 3D space. Okay. Put that back to intensity. Okay. So on the raw data side of things, so I'll just keep going through a few different things we do, and then I'm going to go more in depth into the raw data processing, which is kind of where the title of this talk comes from. So there's some signal processing involved for things like if you've got this echo pulse which is coming back, the LiDAR the laser sent out a pulse, and then it comes back again, and you measure a waveform. You've got to pick the peaks of that waveform to determine what the ranges were, and you can get more than one range per pulse because you might go through several layers, say, of a tree. So this signal processing kind of flavors of stuff that we do. Then there's georeferencing. So that's once you've got all this raw data, you've got to figure out where it is on the Earth. So our aircraft has a highly accurate inertial measurement system and GPS. So those give us accuracy roughly on the order of, say, 10 centimeters, 10 to like 15 centimeters absolute accuracy for the point clouds, which is kind of amazing considering that you are 500 meters up in the air. So this is a typical swath that Okay, so one other thing, we have to figure out how to store and index all this data because we are scanning very large areas and we end up with some hundreds of terabytes worth of point clouds. So yeah, storing those and retrieving them in an efficient way is a fairly interesting thing in its own right. So just to expand a bit on this data here, this is a typical swath. So you fly the aircraft along that length of data. Maybe I'll just... Okay, so there's actually 2 LiDAR systems on each of our planes. You can see the swaths that each of those map out. So from the point of view of the LiDAR system, it's just mounted on a stiff plate next to the inertial measurement unit. So it's just scanning out a fixed kind of, from its point of view, it's scanning out a fixed line with a rotating mirror. So as you fly along, you sweep out a volume. So that's typical aerial swath mapping. And also you get an image which is overlaid. You get to take an image every 5 seconds or something. So that can be overlaid on top of that as well. Okay, so yeah, what I'm going to be focusing on here in this talk is the georeferencing side of things. So how do you make the point clouds as accurate as possible and as consistent as possible with each other? Okay, but before I go back into that, it's hard to read. Just tell you a little bit about a few other things we do because it's sort of interesting, hopefully. Certainly interesting to me. So once you've got this data, you actually want to infer what is there. And I mean, you can. So this is obviously an example of power lines and poles which we've detected. And I mean, this is just an area I extracted out of our data set as a whole. And this is a corresponding point cloud. So as you can see, you don't necessarily get a lot of points on all the geometry. I mean, this is not even that bad. Sometimes you get about 1 point on a pole, or maybe 0 points. So it's an interesting inference problem. You know that the power lines have to be held up by something. So it might it might be a pole, but it could also be a building if there's a service wire or whatever. So all the features which exist in this point cloud kind of talk to each other or have some mutual information with each other. So yeah, it's an interesting inference problem to figure out what's actually there. So sometimes the only hint that you have that there's a pole there might be that, oh, that one's pretty good, might be that there's, well, it's not fitted that well. This might be a different year worth of data from the set of poles and lines I've got here, which actually, yeah, that's exactly the problem I'm trying to solve, this inconsistency. So, yeah, okay. Okay, so that's sort of some of the fitting stuff we do. We also fit buildings, and we've been working on roads and other things. So basically, anything you can imagine in that point cloud, we would like to kind of provide a high level of representation and let people kind of query that data. Yeah, so we approach this as a kind of inference problem. There's also certainly a bunch of machine learning that goes into what we do, and we're kind of going more and more in that direction. Because if you don't try and use the statistics of the data to work out what's there, then you'll end up kind of, well, you'll end up doing it anyway. It's just that you'll look at the data and do something inside here, and then hard code something which is hard to change later when the data changes. So yeah, we definitely need to go in that direction. There's a bunch of robust fitting. Once you've figured out that something might be a power line, then there's some robust fitting to do to actually build a model from that, a power line or a house or whatever. And then, of course, the algorithms are always never perfect. So there's human QA step, which goes in on the back of all of this. Although we certainly go by the kind of philosophy that if a human can do it, then a computer should be able to. We just weren't smart enough yet to figure out how to get those humans out of the loop. It's a pretty mindless task going through and correcting the data. So on top of that stuff, you can do modeling. You can do physical modeling. You could provide a report of where people need to put in stays to keep the poles from falling over. Or you could provide a report for, so one of the problems that transmission line companies have, where they have very the big transmission towers with the really big lines. One of the problems they have is they don't know how much load they can put on those wires, and the load, as you put load on them, electrical load, they sag because they get hot. This is actually the reason you can't put more load on them, because they'll sag down and then they'll violate the clearance regulations. You can't go lower than a certain height. And if you went too bad, then you would just, too low, then of course you just start arcing or whatever. So there's some physical modelling. There's also risk modelling, which we would like to do. We haven't gotten deeply into that yet. Okay. Right, okay, so on to the meat of it, I guess. How are we doing? Oh, that's fine. I better go a little faster, in fact. Okay, so let me just zoom in here. Oops, oh dear. Something funny is going on. Oh, there we go. Okay. Okay, so this is a typical problem we get. Each color here is a separate scan. So when you scan the same area multiple times, this is a lot more times than we would normally scan. This is a kind of control area. But yeah, each time you scan, you get a slightly different position for the georeference data. And you really like those all to be the same. So, I mean, you'd like them to be like that, right? And we'd like to do that automatically. And it turns out that it's much easier to do this more automatically than it is to do it by hand even. You go to a random area and try and put them together by hand. This is a very nice example because it's because there's some roofs and it's easy to see, but if you go to a random place, like there's just a field there or something, then you won't be able to tell how the things should match together. Okay, so, oh, something funny's going on there. Okay, so why would you want to make the match? Well, I mean, it seemed kind of obvious, but from our point of view, you'd like to detect changes between years, for instance. If you're fitting features and you want to kind of augment several scans together to try and get the most points you can have, then you need things to line up so that you can fit things well. Object classification, I'm not sure what I was going to say about that. So some objects are very close to others. For instance, you've got, say, solar cells on the roofs of houses. They're quite close to the plane of the roof. And if you have this fluff on the points, then you might miss them if you have several scans together. Okay, so point cloud matching. Okay, so how do we go about putting those point clouds together? Well, you can do it on a per little tile basis, like you just saw in that little example. And the basic idea is you just go, I want the points in this point cloud to be close to the ones in that point cloud. It's pretty dumb. You just take the nearest point and to every point, you take the sum of the squared distances. You think I need a square in there. Anyway, so you minimize that thing. So T is a translation or a general transformation. In practice, of course, it's not quite that simple. You have outliers, you've got to get rid of those. Point-to-point distances also converges quite slow, so you actually want to do a point to some kind of approximate plane. So you end up with something a little more like that. Let's not worry too much about that. I'm not going to bother explaining it in detail. But basically, you have to do the usual kinds of things that you expect when you have real data. There's outliers and there's funny stuff, and you have to kind of work around that. Okay, so let's go back here. So let's try that. Hope this will work. Okay. Okay, so this is just a little example of the matching process. There's 2 point clouds here, which is a little hard to tell maybe. Oh dear. Datasets. So there's 2 point clouds, that one and this one. and there's a bunch of match vectors. So these are matching down the normals. This is what I was saying, so it makes it a little faster. So basically you just want to minimize, at each step you compute closest points, and then you try and compute a transformation which will make the distance to the point cloud smaller. So as you can see, it can just kind of converge. So by the way, this is running Julia code in the back end to do that transformation. So now all of the little vectors here are, you can hardly see them actually. The little line segments are really short, so things have matched up. So okay, you can do this matching. Let's just get rid of that. Oh, it still wants to keep going. Let's get rid of that. Okay. Okay, so you can do this matching stuff. So this is an area. It's just a screenshot of Google Earth. Each of those stripes there is a flight strip. So we've flown along and captured some data. And each of the color represents like how far away are point clouds from the other point clouds. So you've got this like a point cloud here and a point cloud here, and you've matched them together, and you have a little translation vector between them. So you're taking like 50 meter tiles, and so you can make just a heat map of how far, like what's the error, and make this all different components.
Take some questions. You're about to cross over into that time.
Oh really? Oh dear. Okay. Yeah, okay. Anyway. I haven't even got to the bits I wanted to talk about with package-wise, but anyway, that's okay, I guess.
I fully intend to give them the
time back. Okay. So I've got 10 minutes left, is that right? Or like all together?
7.
Okay, sorry. Okay, so you have all these matches. On their own, they can be a bit outliery and a bit incorrect. So this is like per tile. And also you have things like if you've got a big wide, if you're just taking a scan of a runway or something, it's completely flat. It won't tell you any information about matching in two of the dimensions, only the Z direction has to match. So on their own, those individual kind of tile matches aren't terribly useful. So what we actually do is try and, what we're still working on is setting up a solver to put all those match results back onto the trajectories of the aircraft and fix them up to make all the matches go smaller, basically. So we've got an error spline for our trajectory, the position and attitude of the aircraft at every time, and as you change that, you can change where the points end up on the ground. So you want to basically adjust those trajectories until you get everything matching up really nicely. And coordinate system standards are more annoying than they should be. Okay, so that brings me to the packages, which I will spend just a few minutes on, I guess. In fact, maybe I'll just do coordinate transformations and then do questions.
Yeah, what happened with the time is that the way they've broken it up wasn't quite fair. So
okay.
Actually, the next one says the next talk's not going to start for another 17 minutes. So.
17?
Yeah, 12 by 7.
Right, but I understand. However, if we follow that, then somebody is Huda here yet? He's the one I'm concerned about because he gets.
The last two are multiples.
The last two are multiples.
Yeah.
Oh, I did not know.
Okay.
How about?
So in the process of making all those pretty graphics, I kind of messed myself up and didn't really do a very good job of thinking about what I was going to say about these coordinate transformations, but oh well. So we've done a bunch of packages to help us with the coordinate transformations. So I'm just going to talk about there's a sort of substrate package, and this isn't really my work. I'm just kind of the person who complains on pull requests or something and says, oh, that thing could be like that. And Andy's the one who's done all the actual work for this package. Okay, so this is a sort of substrate for building, a package where you can define a coordinate transformation and it has the information inside of it, and then you can apply that transformation to points and produce other points. So built into this is a bunch of really basic things. So let's just using, whoops, use that. Okay. Ooh. Done. Okay, so we can have a point. We can make a rotation. Whoops, rotation 2D. So some number. This is the very basic thing. So some people may have used, I think there's a affine transformations package by Tim Holly. So that kind of has this kind of idea if you use this transform function to apply transformation to a point, and the transformation's data is stored inside of a transformation object. So this is quite similar. We're just trying to generalize the idea a bit to allow various types of transformations. So you can have translations. You can compose these things. So the kind of essential stuff about a transformation. For our purposes, we'd like to create these transformations with information inside of them, and we'd like to compose them, we'd like to invert them. So you can, compose things. So that will give you a composite transformation, and both of those are affine transformations, so that will put them together into a single affine transformation. Surprise, Andy. Yeah, I was fiddling with this last night. So hopefully that will actually work, yeah. So you can transform points via some composed transformation. You can chain those, you can chain the compositions together as much as you like. And if in the case that these like two sides of the transformation are special, then you can produce a kind of, you can put them together, say like in this case where we've got an affine transformation coming out from rotation and a translation. Okay. Oh, and you convert things, blah, blah, blah. Okay. Oh, maybe I can do that as well. So, not sure if that'll even work. I was hacking on it last night. Potentially. We can try it and see if invenv works. Okay. Yeah, I need to do some more testing. That was late night hacking last night, so inv on affine transformation doesn't work at the moment apparently. Okay, that's probably about enough. I might just briefly mention Geodesy. I thought I was going to spend quite a bit of time on that, but I didn't. The Geodesy packages for doing transformations between geospatial coordinate systems. So you want to convert from a lat-long geodetic coordinate system to a Earth-centered Earth-fixed coordinate system. If you want to convert from one Earth-centered Earth-fixed coordinate system to a different one, all those kinds of things.
Is that for geodesic coordinates?
Yes, that's right. Well, for geodetic coordinates, yeah. So we have those things in there, and we also have the universal transverse Mercator projection in there, which we ported over from Geographic Lib, which is the most, I would guess, is the most popular map projection. So that's kind of handy. And we're intending to use Proj4, which is a C library, and we'll use that for more esoteric map projections and stuff like this. So all of these transformations, we're done, are we?
You're welcome to take over the timing.
Okay, I think we're pretty much done. Okay, so what was I going to say? Yeah, okay, so it's a place for general transformations about the Earth, the Geodesy packages, and we're hoping to add a bunch more things to that, and we need that for all of our stuff. Okay, and getting these transformations right is actually quite finicky. And the derivatives of the transformation. So if you want to do an optimization of the trajectory of an aircraft, you would like to know how changing this part of the trajectory here is going to affect some georeference points. So you'd like to take derivatives of the error state of the trajectory, and you'd like to map those through the whole transformation chain and optimize the thing. So yeah, we support those kind of things. Okay, thanks.
Thank you.
Okay. So I just wanted to mention particularly Andy Ferris, Andrew Smith, they work with me, have been doing cool work on this, and as I said, I've just been complaining on pull requests about APIs and things. And some other guys, Yasin and Sean, started out the Geodesy package, so we didn't originate it. Anyway, thought I should mention that. Oh, jobs, yes, we are hiring. Come work with us.
That's important.
Yeah, okay, questions?
So how do you do object detection? Like how do you distinguish between like a building and a tree?
Right. That would take a long time to describe. So like at the basic level, you can do local feature stuff on the point cloud, so you can kind of compute some local covariance of the point cloud. This is a standard technique.
The edges, like
Well, what we do is I don't know, like, there's heaps of stuff you can do, basically. For imagery, you'd obviously like to use deep neural networks or something, which is what we're kind of digging into at the moment. We're not using production yet, to kind of say, label what's there. For fitting, we do a bunch of hacks, but we're currently developing a system which is a lot less hacky. But you have things like you want to filter the point cloud to kind of remove a lot of the points and only get the ones you're interested in. So for instance, if you're doing finding the roofs of houses, you can filter it based on the local features of the point cloud, and you can end up with mostly just points for houses, the roofs of houses. And then you can do some kind of robust fitting stuff to fit planes into the roofs, stuff like that. So that's the kind of general strategy that we take for fitting things. Yeah, but that's a huge rabbit hole. Yeah. Anyone else?
So this is not really about Julia, but why do the power lines show up so well on LiDAR? Like it seems like they're quite small, so like it would be hard to get with.
They don't always. So you've been seeing some data where it does work quite well, but it depends obviously on what the surface of the power lines are made out of. A lot of them are coated, like the service wires to houses are coated in black stuff, and they're small and sometimes they don't show up. Long lines in outback Queensland made of thin steel wire, you might get 1 point every 10 meters, and we still manage to fit those things. So like might be couple of hundred meters long, and you get 1 point every 10 meters, and you've got to pull that 1 point, and you have 40 points per square meter on the ground, so you've got to pull that 1 point per 10 meters out of, so you've got some sort of ridiculous outlier fraction if you're fitting that stuff. Oh, sorry.
How compatible is the coordinate transformation with ordinary Julia objects like arrays? Or do you have to convert them to special objects like points?
At the moment, it's based on fixed size arrays because it's sort of geometrical, and basically coordinate transformations wants to have an input and output type. The abstract transformation has an input and output type. So it's not currently compatible with, like rotation 2D, for instance, isn't compatible with a 2D Julia array, but it's early days, so I guess we'll have to think about how to make it work well. Yeah. There's thinking to do basically on the API side about how do we support that stuff, and yeah.
How much time does it take to generate all of those points for a particular area of interest?
Do you mean read the raw data file, and or do you mean fly, or do you mean process, or what? Process. So I think the processing code I've got is a little slower than real time. So it should, for that long one you saw way back, go back. For this data set here, something funny is going on there. So for that one, probably, I don't know, half an hour of processing or something. Yeah.
Thank you, and
Yeah.
thank you for being indulgent with my
It's all right.
lack of supervisory skills.
Okay. Yeah.